Welcome back to ECE 441-541A. Today, your homework number 1 is due. Homework number 2 is due a week from Wednesday, and your first exam is coming up a week from Friday. And if you're an online student, you'll want to make sure and register your time that you take the exam with Examity. You also should be getting teams together, communicating, and starting to think about doing lab number 1. That lab experiment write-up is due on October 1st, but you actually are going to be held responsible for that material on exam number 1. So you want to at least understand the material, be able to perform the calculations associated with lab number 1 prior to exam number 1, even though you might execute or write up your lab later and turn it in after exam number 1 because it's not due until October 1. You can sign up for a 1-hour time slot to perform that lab in the stock room of the ECE building, and that's in room 351. And all of the equipment or hardware that you need to execute the lab will be located in the room in ECE 310. Today what I want to do in this lecture, and maybe the second half of this lecture, is walk through a linearization quiz and also then start discussing this concept of linearization. The linearization quiz is as follows. I simply am asking you to give me a yes or no response to the following question, and that is the system linear? And if you're watching this, then what I would suggest that you do is pause the video and then hit play, and obviously then I will start answering these questions and moving forward. Is system A linear or not? Yes or no? Hit pause and make your decision. Hopefully, in this particular case, you said that this system is linear, and I'm not going to really talk about that yet because it might influence your answer to part B. Here's part B, and I want you now to answer this question again. Is the system linear? Here you have a coupled differential equation. You have some dynamics in x, you have some dynamics in y, and the input is u. And I want you to now tell me, is this system linear or not? Pause the video, and when you have an answer, hit play. In fact, this particular video, this system, this coupled system, is not linear. It's not linear not because it's coupled, but because of this product term, a product of two variables, x and y. It could have been a product of x with itself. It could have been 5x squared. That would have made it nonlinear. It could have been x times x prime. That would have made it nonlinear. Or it could have been u squared, or it could have been x times u. That also would have made this particular system nonlinear. Part A only contains linear scaled variables. Variables that are scaled with a 4 or a 5 or a 1 or a 7, a -7, but nothing that is a product of terms involving x, x prime, u, or u prime. And so A is a linear system for that reason. System C. Let me know if this system is or is not linear. Is the system linear? Yes or no? Pause the video, think about it, and when you have your answer, hit play. This particular system is in fact not linear. Is the system linear? No. And the reason it is not linear is because we now have this sign, which is a nonlinear operation on one of our variables that is in the equation. So here we have sine of x prime. We could have had 6x prime plus 7 sine of x. That also would have been a nonlinear system. Or it maybe instead of having the sine, maybe it was the square root of x prime. That also is a nonlinear operation on one of the variables, and that would have made that particular system nonlinear. So the reason that C is nonlinear is because we have a nonlinear function being applied to one of our system variables or quantities. In this case, it's a second order differential equation, but it's also nonlinear because we have this sine of x prime happening. One more. Part D on is the system linear. Look at it, pause the video, and when you have your answer, hit the play. So pause your video and make your answer. This particular system is in fact linear, and now you're saying, well, it has a sign just like system C has a sign, but now that sign is actually a function of the independent variable t, which makes this a time-varying system. All of the other systems were actually time invariant. The coefficients, the scaling were not a function of t. Here, this sine of t is actually a time-varying coefficient, but it's still a linear system. So this is a linear time-varying differential equation with a coefficient of sine of t. Most of our systems in this class will actually be linear time invariant so that we can perform the analysis that we want, and that's where we are going to go now in this particular video, is trying to understand this linear system, and if it's not linear, what do we do with it? So now let's get into this topic of linearization, and the background before we really start talking about linearization is let's go ahead and define a linear system. A linear system actually satisfies two properties. These are AND properties, not OR, but you have to have both of these happening with the right-hand side of your differential equation. And again, x and u could be vector quantities. But for that system, x prime equal f of x and u, for that to be a linear system, it needs to satisfy superposition, which means if you had an argument of x1 plus x sub 2, where x1 could be a vector of x's and x sub 2 is a different vector of x's, their sum is, and operating on the taking the functional form of their sum can be equal to or is equal to f of x1 plus f of x2, then it satisfies the additivity property or superposition. Homogeneity is similar. It's now, though, that if we scale the argument of our function of our right-hand side, that scalar actually can slide through the function, and now f of alpha x is the same as alpha, or a scaled version of f of x. The mental image that you might want to be thinking of is really this concept of a linear function. We need to make sure that it's going through the origin, though, in this case, and now we have f of x naught is at a particular point on our line, and if we now operated on f of x sub 1, that now would give us f of x sub 1, and those two functional forms of f of x are linearly related based on the relationship between their arguments x sub 0 and x sub 1. Now, in what we've done so far in this class, we've been focused actually already on linear systems. And you can see that on the right hand side. Now instead of f of x u in terms of its description, we're getting a little bit more specific with how we are representing that f on the right hand side. And in this case, it's a matrix times the state vector x plus another matrix times the input vector u. Here in this second order example, I'm simply looking at one input and two state variables, but in general, as long as you have a matrix times an x plus a matrix times u, that's now a linear system. And in this class, those coefficients or those matrix element entries will not be functions of time. If they were, it would still be linear, but it would be time varying. In this case, if you don't see it with the matrix representation, go ahead and multiply out the right hand side, and hopefully you can now see that making up the time rate of change of x1 or the time rate of change of x2 on the right hand side of that set of equations, you do not see any product terms, anything like an x1 times an x2 or an x1 squared or an x1 times a u. You don't see any product terms, and you don't see any nonlinear terms, nothing that looks like sine of x1 or square root of x sub 2. Those are not present on the right hand side, and for that reason we have a linear system when we have an x prime equal ax plus bu. And that's really the kinds of systems we want to be dealing with in this class. Now that said, linear systems, usually we have to create those. In reality, most systems are nonlinear, and let's just look at some common nonlinearities that you might already have experienced. One is amplifier saturation. A lot of your devices or expressions or dynamical systems, actually, if you push them hard enough, will move out of a linear operating range. And in this case, you can see that instead of always being sort of linear near the origin, it starts to bend, or in this case it looks somewhat exponential, but you now have saturation happening at higher and higher levels of the independent variable x. A dead zone is another nonlinearity where maybe the functional form doesn't possess any value in a given range. Now maybe the range is some value x1, and maybe here is minus x sub 2, and between that interval f is 0. And that's not linear. It may be linear outside of that dead zone, but in this case, because of that dead zone in it being in existence, our system, if the right hand side has this kind of functionality, is going to be a nonlinear system. One more nonlinearity that's common is a backlash nonlinearity, and now you might, if you're following along here, you might think about what happens with gears. And one way that I like to think about that is, suppose you now view your two hands as if those are meshing gears, and let's say that your right hand, you want to now move it in a clockwise direction. So now what I'm suggesting that you do is you interlace your fingers, and now push your left hand fingers in response to moving your right-handed fingers in a clockwise direction. I have my palms facing me in my eyes, and now I'm moving my right hand in a clockwise direction. Suppose you now stop that and keep your left hand fixed, but now try to move, and now I'm assuming that your fingers are not tightly together, but there is some space or gaps between your fingers, and now your right hand going counterclockwise might actually move, before your left-hand fingers start to engage again and move in response. And that's what happens when you have gears. If there's any kind of gap or tolerance between your gears, which there will be, but depending on the situation, is that going to be significant or not, and you have to worry about those meshing gears in your design and account for that nonlinearity. In this particular class, what we are concerned with is playing with or working with linear systems, and the tools that we are developing are definitely designed or based upon having a linear system. So to do our analysis, to perform our design, we have to be working with linear systems in this class, and if they are not, what do we do? What do we do if we have nonlinearity in our system? Well, the answer, earlier in the day, that answer was chocolate, but now it's actually linearization, which is the correct answer. You now want to linearize this nonlinearity in your system, and that now gives us or allows us the opportunity to work or use the analysis and design tools that we are developing in this class. So if somebody does give you a nonlinear system, the first thing that you probably will do in this class is linearize it about a particular operating point, and then perform your design on that linearized version of the nonlinear system.